Okay, so I'm Mitchell Larger,
I'm Colin Buckley.
and we're doing electric vehicle charger utilizing AC to DC rectification. So in this presentation, we're just going to cover the project objectives of our project, a few key points that we wanted to hit along the way. We're going to talk about the background and some introduction to EV charging stations. We're going to talk about our solution and how we propose to make it better in our simulation. We're going to talk about the outcome and those simulation results that we got, as well as the project timeline and some lessons learned along the way. So a little background about EV chargers. Obviously, electric vehicles are becoming more and more popular on the roads today. So consequently, the need for electric vehicle chargers is also becoming more important. Companies like Tesla, ChargePoint, and Ionity are some of the leaders in the market for this market of EV charging stations. And so, as you can see here on the right, there's three ways to categorize or classify EV chargers. A level 1 charger is a trickle style charger, and it runs on 120 volts. This is your slowest charger, and it's your least efficient, and you only get about 2 miles of range per hour of charging. So not very much range per hour of charging. Level 2 runs on 240 volt supply, and this one will get you about 10 to 50 miles of range per hour of charging. So a little bit better than level 1. And then level 3 classified chargers are considered fast chargers. These are the ones that we just designed and simulated in our project. And they run on a 480 volt supply. So level 1 and level 2 chargers you can purchase and have in your home, as well as public charging stations. Level 3 chargers, because they run on a 480 volt supply, obviously people don't have that at their house, so they're less common in homes and can be found in public charging stations throughout the country. So our solution for this project was to design a full wave AC to DC rectifier for EV and hybrid vehicles. Our rectifier will take a high voltage AC supply from the grid and output a DC supply that can be used by these charging stations. And as you can see down here, this is just a simple block diagram of our circuit design. We take AC power from the grid, step it down through a transformer to a voltage level that is usable by the EV chargers. And then the rectifier, capacitors, and regulator all filter that AC signal and convert it to a DC signal that can be used to deliver power to the load. And so during this project, we wanted to hit 3 main objectives. The first of that being a conversion efficiency of 92 to 95%. A high efficiency reduces heat loss and improves charging time, like you see in those fast chargers, the level 3 fast chargers. Our second objective was to limit the ripple voltage to less than 50 millivolts. And then our third objective was just to simulate our rectifier design and measure the outputs or the simulated values versus our calculated values.
All right, so this is a full circuit we ended up putting together where we take the power from the grid, step it down, send it through a full wave rectifier bridge, so then we can deliver power to a car. So before we started getting values for the circuit, we knew some kind of like global variables we wanted to use. We wanted the output voltage to be 480 volts to align with realistic EV chargers, the power to be realistic to real EV chargers, which was 140 kilowatts. And we ultimately had to pick a grid voltage. So we used a real world example we've seen in the field, which was 13.8 kilovolts. These are the calculations we used to basically find all the values throughout the circuit. So we kind of calculate what our output current would be, our resistant load would be. Using the efficiency we wanted to have in our project objectives, we were able to determine our AC power from the grid and everything through, and ultimately we're able to calculate the capacitor value. So we had all the values we needed for our circuits, and then we could simulate it through multi-sim. And this is a circuit we threw together in multi-sim. This was a great tool for us to use so we could verify that we, one, calculate everything correctly in our original circuit, as well as two, we would get a visual representation of what our output graph would be at V out. So on the next slide, we can see we were able to determine our output voltage to be 453 volts and our output current to be 274 volts. And you can see how the output current is pure DC. So we ended up wiring everything correctly, and it was perfect visually. But on the next slide, we saw that there was a bit of an error between our calculated and simulated values. So we decided we wanted to see what the percent error was from calculated to simulated. So for our voltage, we found that there was a 5.91% error, and then for our current, there was a 6.18% error. And that's not ideal, but it is just circuit simulation where we could go more in depth and figure out where the issue actually lies, which could be in the diodes.
So this was our project timeline. This was a rough estimate of the timeline we followed. You can see that we spent about a week on each of the different prospects or sections of our timeline, starting with the proposal. And then we did our research on the converters, as well as the circuit design and simulation. And then these last couple of weeks, we're going to be finishing our presentation and our report. Some of the lessons we learned along the way, like I mentioned earlier, the electric vehicle market's booming. It's only going to continue to grow. And so this type of project is very marketable. In our situation, however, like Colin mentioned, our percent errors were a little too high for our liking. So our specific design may be less desirable because of that, but the overall project is very marketable. And then a lesson that we learned along the way was that diode choice is really important for the design of the rectifier circuit. So we considered many different options, but finally landed on the right one.
So, like I said, EV Tesla chargers will continue to grow in popularity as more EVs and plug-in hybrids come on the market. We were able to design our own AC/DC rectifier for a Type 3 charger, and we were able to simulate it to see how well we were able to design our AC/DC rectifier. While our simulation was successful in the fact that we were able to convert our AC signal to DC, we experienced a greater percent error from our calculated simulated values than we originally expected, which ultimately makes our project not super marketable, but it is a great step in the right direction for future projects.
And then here are some of our references. Thanks.
Thank you.